Good morning. So welcome to my talk. I'm really looking forward to give you a bit of insight on what I believe to be the future, the inevitable future of how we build software in the coming decade. And I have a bit of a concurrency and distributed systems background and doing work with microservices mainly, but I also have some experience building large-scale business systems. So this session will be more from my sort of microservices perspective. So I work for a company called Lightbend. How many of you know who we are? Wow, nice, good to hear. And I just want to give you a little bit of an overview on what I'm going to talk about. And it's going to be in a similar vein as the previous session. It's going to be a bit of time travel. So we're going to have a look at some past events, some current events, and some coming events, and some possible future events. So we're going to do a bit of event stream processing here. So are you ready? Awesome. So first, a bit of history. Let's look at some past events. And this is definitely not going to be a complete history of data processing because that would probably take the entire day. But I want to highlight some important parts. Do you recognize this? Anybody done some offline batch processing at some point in their career? Still doing it today, perhaps? What's interesting about these is that they're all in use today. And by offline batch processing, I mean stuff like processing files or running jobs on top of an RDBMS or something, which is typically something that you trigger manually and runs on a single server or a single workstation. Then came the era of big data, and we needed to scale out, parallelize processing. So think Hadoop and other MapReduce style frameworks to deal with more data. But it's still basically disk to disk, and the big issue with batch processing is the latency aspect of things. So you can't necessarily start with the first element that you received until you've received the last element. So then we had Lambda architecture that tries to solve the latency problem by running an adjacent stream processing engine to provide some intermediate fresh data until the batch processing engine catches up. So this is a bit of history, right? And you all know this. But there's also a parallel history of doing services, right? I don't know, how many of you are familiar with these sort of classic client-server applications where the client is essentially co-developed with the server because they are very linked together, very coupled. You can't necessarily evolve them separately. Anybody heard of Corba and DCOM, Microsoft DCOM? Yes, yes. So Corba tried to solve the problem having these sort of coupled clients and server by introducing the interface definition layer. So essentially having a schema-first style of development so that you can derive clients in different languages and different platforms so you can have interoperability. And DCOM was sort of a competitor to Corba at the time. Then came Enterprise Java Beans and Enterprise Service Buses. Enterprise Java Beans and N-tier architectures. So typically the N was 3. So you had one part was the presentation layer, and then you had the business layer, and then you had the persistence layer, but they're running separately. And then came service-oriented architecture and enterprise service buses. So think WS Star, web services, SOAP, things like that integrating through enterprise service buses. Does this seem familiar? And of course, it wouldn't be complete if I didn't mention HTTP APIs and REST APIs. And to be honest, most REST APIs are essentially HTTP APIs because getting the entire REST part right is not necessarily easy. But the good thing with HTTP as a protocol was that it was really good at traversing networks. So it's still being heavily used. So that leads us to today. So what do we have today? Well, if we were to look at the menu, the catch of the day would be live stream processing and microservice architecture. So live is near real time, but if you say real time, then the hardware people will be upset. And so we at Lightbend, we call it fast data, but it's having data that is processed as soon as possible when we receive it. And the cool thing is that doing stream processing means that we can very neatly do data cleanup, aggregation, enrichment, transformations, analytics, very, very popular today, but also create projections and views of the data. So that's really good for that. But on the microservice architecture side, we have two main tracks of microservices. One is the classical sort of RPC style microservices, where you have requests and responses, and then you have something which is called evented microservices, which is services that consume and produce events. And what microservices are good at is access control. You can define encryption, authentication, authorization, validation. You can have a centralized place or a given place to put your domain logic, right? It's encapsulated within your service. But it's also really good at delivering data to the outside of the system. Think GET requests in HTTP. So if this is what we have today, then I think that we have some shared requirements for these two different things. Because they both need to be available. When you have a live stream processor, it needs to be available. Otherwise, it's not going to be live, right? But if you have microservices, they're going to have to be available as well. So that means they need to be elastically scalable. We need to be able to have more of them so that we can handle more load, or less of them to conserve resources. They both need to be resilient and self-healing and deal with failures that occur all the time, especially in a live system. And of course, if we build our systems with these things, we need them to be separately updatable and upgradable. And they can only be that if they are decoupled. So I think that they all have the requirements of running as reactive systems. And reactive systems tries to achieve availability, responsiveness, being able to respond, both under failure and under load, by being message-driven, by using messaging as a core part of the architecture. Because fundamentally, every single system is a complex system. The very definition of system is that it is complex. So we have many components within a system, and we need to treat them as a system. So we need to deal with how do they interact and what happens when things go wrong and what happens when we have additional load. And using messaging means that we don't necessarily hard code where things live or where things are, because we can route messages. Related to this is the concept of reactive streams. So once you have a system of independently running components, then you don't want to have the entire system to fall over because one component produces data faster than another component can receive data. And within every single large system, this will vary over time. It's a dynamic problem. Sometimes this component is faster, sometimes this other component is faster. So we need to think about how data is handed between components. So reactive streams is a standard which is in JDK 9 under Java Util Concurrent Flow, which deals with how do we send data asynchronously between components with non-blocking, because we don't want to tie up threads in our runtime, non-blocking back pressure so that we don't overload individual components. So it acts as a bridge of sorts between components. And what's interesting about that is that if you have other protocols, like if you go over a network, then you can sort of go into the TCP windowing, so because TCP also has flow control, and you can layer that on top of reactive streams so that you can get a flow control over the network. So what do we have here? We have stream processing stages, which can be both stateless and stateful. The stateless part is less interesting, but of course that exists, so we need to be able to support that as well. And we have these microservices that are both RPC style and evented. But also, I think one really important part is when we are data-driven, it's not only data. It's not just ones and zeros and we don't know what it is, because that would be extremely meaningless, right? I think most data is actually evented data. It is linked to some sort of event. So I think if we have events, then we should be thinking about events. Because if we are data-driven, then our data becomes our API. So if we think about that, then we need to be more structured with how we deal with the data. And of course, we need to be able to both interpret data as events, but we also need to serialize or create data from events. So that's where the schema and codec thing comes from. So just to define what an event is for the sake of this presentation, think of it as an immutable recording of an observation. We can discard or disregard events if we're not interested in them. But if we do accept them, then we can't just retract them. But we can invalidate them with new events. But we typically don't want to delete events, but it can be necessary for legal or for moral reasons. But the interesting part of being event-driven is that knowledge grows or accrues with every single message received. We know more for every single message, every single event that we receive. So, I just invented this notation, so don't be worried. I will go through it. What's interesting about evented services is that if you think about it, you have some behavior and some current state, and you have a new event, and you apply that to the behavior. You apply the state and the event to the behavior, and from that you yield a new behavior and some effects that will produce more events and the next state. So I consume an event, and I have memory, so I have my own state, and from that there are possibly more events created, which is my output. Interesting. Very interesting. They're stream processing stages, right? It's just a stateful stream processing stage. So I think in the near future, there is going to be a convergence between stream processing and microservices. And that's sort of the premise behind my keynote, so I hope so. Right? They are starting to look quite similar when you look at it like this. So is this the solution? We just have evented microservices being stream processing stages, right? We lift the evented services into the stream processing pipeline, and then we're done. Well, I think we're forgetting a really important part of microservices, and that is the request response case. And I think we can do better. So RPC style services are slightly similar here, right? We have some current state, and we apply a command and the state to the current behavior. And command, you can think of it as a request, because it's typically a request. From that, you get the new behavior and some effects that will produce the new state. And by effects here, think of things like storing it to durable storage, because we want to do that, or we want to reply to this request as an effect. But they are slightly similar, right? If you look at this. So an improved solution here would be if we can lift the RPC service into a stream stage by lifting input events into commands and submit them to the microservice. Then we can capture the response and convert the response as output events. So essentially, we're creating a wrapper on top of any microservice to lift it into an event pipeline. But what if we could derive microservices from data streams? Because now we have the capability of lifting microservices into a stream pipeline and RPC style as well. But what if we could go in the other direction? What if we could derive microservices from data streams? What would that look like? So as an example, ingestion endpoints. So when you need to receive data into a system, it's a very common use case, right? What if we could derive microservices? Because microservices are really good at receiving requests and responses. So if we have some sort of schema for the data that we're going to receive, and we have some requirements regarding authentication and authorization and encryption, etc. We might also have some requirements on which protocols or transports that we support. Perhaps some are HTTP, some are MQTT, what have you. And we have a destination of that information. We need to receive the data, but we also want to produce it somewhere else. Perhaps we could just derive a microservice on the edge as an endpoint that feeds that data into the pipeline. But also in the other direction, right? We want to be able to provide projections as a service. And the very simple case is if you have a data processing pipeline that you want to be able to expose as a microservice, let's say that it produces some sort of aggregate, then if we only have a schema for that, we have requirements on authentication authorization for who is allowed to consume this data, some transports for that as well, and the source of this aggregate. Then we should be able to just derive a microservice from that serves that projection. But we could even make it more complex, right? It's not only just being able to receive the current state of an aggregate, but what if we had the same thing we had before? So we have some schema, some authentication and authorization requirements, some transports, a source of the data, perhaps a store to store the projections. Perhaps you want to store them in a time series database, you want to store them in a graph database, or whichever database makes sense for the use case. And if we only pair those with an upsert style query, an aggregation, and any number of equivalent SQL or select statements, if you so will, selections, then we could create aggregators and create individual microservice projectors for each of those queries that we can deploy and upgrade independently. So I think that we see a bit of a unification here, that we can run microservices as a part of a stream processing pipeline, and we can run a stream processing pipeline as a part of running a microservice-based system. We can now essentially have the best of both. Because now we can independently upgrade parts of our system. Our stream processor needs to be updated, we can do that. Those microservices need to be updated, we can do that. Super interesting. But how do we develop these applications? What do we need to do differently? Or what can we improve so that we can write systems that do this? Because, I mean, the goal is always to focus on the business problem, right? Well, clearly we need to have some sort of deployment orchestration, because if we're going to run different microservices and different stream processing pipelines, then we need to be able to deal with that orchestration of deploying those. If we treat events as the API between components, then I think we need to do better in terms of designing events, evolving events, knowing which events that we should be storing and which ones that we shouldn't be storing. How do we version them, and how do we develop using events? And there are two things that I think are promising in that space, which is one is events first, domain-driven design, and one is event storming. And I think there's a book on event storming coming out by Alberto Brandolini, and I think it's Russ Miles who has written a bit on events first, domain-driven design. But I think we can also do better in terms of continuous deployment, because the more components that we have that do different things, the more important it is that deploying them becomes automatic and rolling them out. And I think that if we are able to derive things and create them by just using metadata, then we can have the metadata also drive the continuous deployment and generate these things. And we can decide to use the right tools for each single component in the system. It's not all or nothing. So what lies beyond this? Well, I can't really necessarily see into the future, but I think there's one thing that I would say is beyond that. And that is extending this style of creating systems all the way to the edges of the system. Because I think right now there's still a bit of focus on the system is what's inside of the data center. And then everything outside of the systems is clients. But I think that every single component that communicates with a system is a part of that system. And with more and more clients, both machine clients and sort of human clients, we need to do more data processing close to the edges. So edge computing, doing analytics and stream processing on the actual devices in order to scale the system. So essentially growing out to the edges in terms of how you think about the system. Because there are some huge differences when you come to deploy things on the edges. Some things you might not even be able to upgrade. Some things are only upgraded when someone else decides that it should be upgraded. So you have to think about things a bit differently. This is sort of the end of stream for this talk. But I hope I've convinced you that it's possible to unify these two different architectures or styles of doing software development. And I think I know that because I do have some working code that does this. So I hope that this is not only a personal dream, but this is actually possible. If you want to know more about the technologies that we create and use at Lightbend, here's a couple of links. I'm really happy that you all attended today and have a great conference. Thank you.